252 million years ago, 96% of all marine species gone. 70% of all land animals gone. 57% of all biological families on the planet gone forever. The oceans emptied. The land turned to desert. Earth lost almost everything alive in a span of time that geology can barely even measure. This wasn't an asteroid, not a single catastrophe, not one moment. This was a slow and inevitable destruction of everything. And it lasted long enough for every living creature on the planet to feel the world dying around it. Scientists call it the Permian extinction, or simply the Great Dying. And even now, after 70 years of research, they still argue about the details of what happened. 4 questions we're going to answer. First, what exactly killed 96% of all life? One cause or many? And could it happen again? Second, which species disappeared forever? What exactly did Earth lose? And how different might the world have been if they had survived? Third, who survived? And how is that even possible? When almost everything dies, what do you need to have in order to stay alive? And fourth, what can knowing about this extinction give us today? Why are scientists studying events from 252 million years ago publishing papers about the modern climate crisis? The answers are coming. To understand the scale of the catastrophe, we first need to understand what the world looked like before it. 252 million years ago, Earth looked different. All the continents gathered into one supercontinent, Pangaea, a massive landmass stretching from pole to pole, surrounded by a single global ocean called Panthalassa. The climate was warm, but uneven, coastal zones lush and fertile, the interior of Pangaea a dry, scorching desert that rain barely reached. And in this world, life was thriving. The Permian period lasted nearly 50 million years before the catastrophe. In that time, evolution had built complex ecosystems, both on land and in the ocean. Forests of primitive trees, reef systems in warm seas, hundreds of species of reptiles, the first ancestors of mammals. And to feel what was actually lost, let's meet one inhabitant of that world. Dimetrodon. Not a dinosaur, though it looks similar. A reptile with a massive sail on its back that could reach 3 meters in length, one of the most successful predators on the Permian land. It lived in a complex ecosystem. It had its own predators that threatened it when young, its own prey, its own place in a food chain that had been building for millions of years. Dimetrodon did nothing wrong. It simply found itself in the wrong place at the wrong time. This world took 50 million years to build. And then it started. Not all at once, not with an explosion, but gradually, like a quiet verdict being handed down. Around 252 million years ago, in what is now Siberia, volcanoes began erupting. But not ordinary eruptions. What geologists call the Siberian traps is one of the largest volcanic events in the history of the planet. Lava covered an area larger than modern Australia. The eruptions lasted not days, not years, thousands and tens of thousands of years. And along with the lava, gases rose into the atmosphere. Carbon dioxide, sulfur dioxide, methane, chlorine, fluorine, in quantities that are almost impossible to imagine, 200 times more. But what does that actually mean? A study published in the journal Science in 2020, led by Benjamin Black, showed that the total volume of carbon released by the Siberian traps may have exceeded 100,000 gigatons. For comparison, all of human activity since the beginning of the Industrial Revolution until today has released around 500 gigatons of carbon into the atmosphere. The difference, 200 times over. That means the Siberian traps, in just a few thousand years, released as much carbon as humanity would if we burned every piece of coal, every drop of oil, every cubic meter of gas on the planet 200 times in a row. The scale is so enormous that any comparison sounds absurd. And that's exactly the point. The atmosphere had never received that volume of gases in such a short time. And the consequences came in waves. The first wave, ocean acidification. Carbon dioxide dissolves in water and forms carbonic acid. The ocean began to acidify rapidly by geological standards. Research by Jonathan Payne's team at Stanford, published in the journal Science, showed that ocean pH dropped by approximately 0.7 units. That sounds like a small number, but the pH scale is logarithmic. A drop of 0.7 means acidity increased fivefold. For organisms with calcium carbonate shells and skeletons, that's a death sentence. Limestone dissolves in acid. Corals, mollusks, brachiopods, their homes were literally dissolving around them while they were still alive. The second wave, heating. The greenhouse effect from volcanic gases drove up the planet's average temperature. Studies of the isotopic composition of conodont teeth, tiny extinct marine organisms, published in the journal Science in 2015, showed that the surface water temperature of the tropical ocean may have reached 40 degrees Celsius. To understand what that means, think about what's happening to reefs today. The heat waves destroying the Great Barrier Reef right now are happening at 29 to 30 degrees. Most marine organisms can't survive even 35. The Permian tropical ocean was 10 degrees hotter than what's already killing our reefs today. And that temperature didn't last a week like a modern heat wave. It lasted thousands of years. For most marine life, that was simply impossible to survive. The third wave, anoxia. A warm ocean holds oxygen poorly. The higher the temperature, the less dissolved oxygen in the water. At the same time, dead organic matter raining down to the sea floor decomposed and consumed even more oxygen. The deep layers of the ocean turned anoxic, completely stripped of oxygen. And then the anoxia began rising, to the middle depths, to the surface. Fish suffocated in the open ocean. Animals that had managed to survive the acidification and the overheating were now dying of suffocation. The fourth wave, land. On land, its own kind of hell was unfolding. Acid rain from sulfur dioxide ate through forests. The ozone layer, the shield against ultraviolet radiation, was nearly gone, destroyed by the chlorine and fluorine from the volcanoes. Ultraviolet radiation killed plants and small animals directly on the surface. Temperatures at the equator may have exceeded 50 degrees during the day. Most large land animals had nowhere to go and nothing to breathe. And there was one more factor that turned the catastrophe into a sentence with no appeal. Pangaea, one supercontinent, one ocean. In most ecological disasters, some regions suffer less and become refuges, islands, mountain ranges, polar zones. But Pangaea meant that heat zones, acid rain, and suffocating air covered almost all of the land at once. There was no other continent to migrate to. No island where conditions stayed normal. The planet's geography had become a trap, and no animal could escape it. One supercontinent, one ocean, nowhere to hide. That's what makes the Permian extinction unique among all 5 major extinctions in Earth's history. And here's what makes it even more so. It struck everything at once. Marine and terrestrial, predators and prey, large and small, plants and animals, microorganisms and complex ecosystems. There was no safe niche, no place to wait it out. A study published in the journal PNAS in 2019 by Jonathan Payne's team showed that ecosystem recovery after the Permian extinction took 5 to 10 million years. After the extinction of the dinosaurs, recovery took less than 3 million. The Permian catastrophe was so deep that even after conditions improved, the living world couldn't recover, because almost no one was left to do the recovering. Earth didn't just lose most of its species, it lost the very ability to bounce back quickly. And that's exactly why scientists studying these events are publishing papers about today's climate crisis. Earth has already been through this. It left us a record. And in the next part, we're going to find out what exactly was lost and who survived. Earth, before the catastrophe, was home to creatures that would never exist again. Not just species, entire evolutionary branches. Nature's experiments that ran for millions of years, erased in a geological instant. Let's meet some of them. Trilobites lived in the oceans for over 270 million years. They survived 2 previous mass extinctions. They watched continents form and break apart. They saw entire groups of animals rise and disappear. They were so successful, they seemed permanent. Trilobites were arthropods with hard, segmented shells. Eyes made of calcite crystals, the first complex eyes in the history of animal life. Hundreds of species, from microscopic to the size of a human palm. Predators, filter feeders, scavengers. They filled almost every marine niche there was. 270 million years of evolution survived everything, and then vanished completely, forever. No descendants, no related lineage that carried them forward, just an ending. Gorgonopsians were the saber-toothed tigers of their time, apex predators of the Permian land, active, possibly warm-blooded, with complex social behavior. Picture an animal the size of a large lion, a skull where the jaws take up half the space, fangs up to 30 centimeters long, a posture closer to a mammal than a reptile, limbs directly under the body, not splayed out to the sides. A Gorgonopsian didn't crawl, it walked. It pursued, it attacked. The entire Gorgonopsian group went extinct during the Permian extinction. Not a single species survived, not a single descendant. This evolutionary branch simply snapped in the moment of greatest crisis. The most powerful predator on land turned out to be the most vulnerable to conditions where power meant nothing. Picture the last one. Somewhere in the Permian desert, the last Gorgonopsian was alive. The most powerful land predator of its time. It didn't know it was the last. Maybe it was searching for prey that had already disappeared. Maybe it was searching for other Gorgonopsians that no longer existed. The strength that had saved millions of generations before it was useless against the slow suffocation of an entire world. It left no descendants. It left nothing. And that is the bitterest truth of the great dying. Most people think Dimetrodon was a dinosaur. This is one of the most common mistakes in paleontology. Dimetrodon is actually closer to mammals than to dinosaurs. It went extinct during the Permian extinction, 40 million years before the first dinosaurs ever appeared. That means the gap between Dimetrodon and T-Rex is larger than the gap between T-Rex and us. Dimetrodon was a predator about 3 meters long with a large sail on its back. Those bony extensions of the vertebrae, covered in skin, may have served as a heat regulator or as a way for individuals to communicate with each other, or both. Scientists still argue about it. It ruled Permian ecosystems for millions of years and disappeared along with its entire world, leaving no descendants, leaving nothing. Rugose corals built reefs for nearly 200 million years, complex colonial organisms that created entire underwater cities, ecosystems that thousands of species depended on. After the Permian extinction, they were gone, completely. The corals we see today are a different group. They emerged after the catastrophe. Evolution was forced to reinvent reefs from scratch. For tens of millions of years, the ocean existed with no reefs at all. Blastoids, echinoderms resembling sea lilies, also disappeared completely. Another branch that had existed for hundreds of millions of years, cut off in a single geological instant. This rarely gets talked about, but the Permian extinction hit even the insects. 8 orders of insects went extinct entirely. This is the only mass extinction in history to cause significant losses among insects, a group that has survived literally everything else. And there's one detail about the insects that reframes everything. Some of those orders had existed for over 100 million years before the Permian extinction. They had survived the appearance of the first fish, survived the Devonian extinction, survived animals moving onto land, survived everything nature had thrown at them up to that point. The most resilient group of animals in the history of Earth. And even they didn't make it. When insects die, everything dies. Pollination, decomposition, food chains. Insects are the foundation of land ecosystems, and that foundation cracked. 100 million years of survival through everything. And then, no. If that doesn't convey the scale of what happened, nothing will. But the most terrifying part isn't the moment of death itself, it's what came after. Researchers found in the geological record what they call the dead interval. 5 to 10 million years of rock layers containing almost no remains of large organisms. The ocean and the land still existed, but almost nothing lived in them. The planet was breathing, but silent. Millions of years of near total quiet. Millions of years of an empty Earth. And then, out of that silence, something new began to appear. But what exactly? When 96% of all life disappears, one question emerges. What exactly did you need to have to be in the 4% that remained? The answer isn't simple, and it isn't always fair. Sometimes the strongest survived, sometimes the smallest, sometimes those who happened to be in the right place, and sometimes those who were so unremarkable that the catastrophe simply didn't bother with them. If you had to pick one animal that represents survival after the Permian catastrophe, it would be Lystrosaurus. And it looks exactly the way you'd imagine an animal that simply survived, rather than triumphed. Lystrosaurus was a therapsid, about 1 meter long, weighing around 100 kilograms, herbivorous, no fangs like a Gorgonopsian, no sail like Dimetrodon, no armor. Nothing remarkable about its size, just a stocky, ungainly animal with a beak and 2 small tusks that dug through the earth looking for food. Before the catastrophe, it barely showed up in the fossil record, one of many, nothing special. And after, it dominated the southern half of Pangaea for millions of years at the start of the Triassic. In some locations, 90% of all land vertebrates belong to this single genus. To understand what 90% actually means, compare it to what we know today. Today, humans and our domesticated animals make up around 96% of all land mammal biomass. Ecologists consider this an unprecedented level of dominance and a serious warning sign. But Lystrosaurus achieved the same thing and then some after a catastrophe that wiped out 96% of all life. One unremarkable genus filling an empty world. This is the only moment like it in the history of the planet, and it lasted for millions of years. Lystrosaurus did what humanity has done. It filled all available space. But unlike us, it did it after the entire previous world had vanished. Why did it survive? Several reasons. First, burrows. Lystrosaurus dug burrows and sheltered underground. Underground means more stable temperature, less ultraviolet radiation, cleaner air than the surface poisoned by volcanic gases. Second, a barrel-shaped chest with large lungs that allowed it to survive on lower oxygen levels. Third, group behavior and tolerance for a wide range of conditions. Fourth, and simplest of all, it ate whatever it found. No pickiness, no dependence on specific plants or conditions. Unpretentious, flexible, willing to eat whatever was there and live wherever it ended up. In a world where all the specialized predators and grazers had disappeared, those qualities turned out to be the most valuable ones of all. Among the few groups that survived the catastrophe were the cynodonts, small therapsids, relatives of mammals, smaller than gorgonopsians, less noticeable, but with several features that turned out to be decisive. First, size. Small animals need less food. In a world where food chains had collapsed, that was an enormous advantage. A small animal can survive on what a large one wouldn't even notice. Second, possible warm-bloodedness. Studies of cynodont bone structure show signs of rapid growth characteristic of warm-blooded animals. Warm-bloodedness allows you to stay active at lower temperatures. In a world cooling unevenly, that could have been critical. Third, omnivory. Cynodonts ate plants, small animals, insects, and anything else they came across. No specialization, no dependence on a single food source.
All modern mammals are descended from cynodonts, including humans. You are a descendant of a small, undemanding animal that survived the hell of the Permian catastrophe. Not through strength, through flexibility. Among the reptiles that survived, the archosaurs, small and barely noticeable during the Permian, but after the catastrophe, they inherited an empty world. Crocodiles are descended from archosaurs, and birds, and dinosaurs. The entire Mesozoic, the age of dinosaurs that lasted 180 million years, was only possible because archosaurs survived the Permian catastrophe. Without the Great Dying, there would have been no dinosaurs, and possibly no us. In the ocean, survival had its own logic. Freshwater fish were almost unaffected. Why? Fresh water buffers acidification differently than salt water. Enclosed bodies of water are less sensitive to shifts in temperature and chemistry than the open ocean. Fish living in rivers and lakes simply didn't experience the horror playing out in the open sea. Organisms that could tolerate a wide range of conditions also survived. Not specialists, generalists. Not those perfectly adapted to one set of conditions, but those tolerant of many different ones. Bivalve mollusks, snails, some echinoderms. They survived not because they were stronger, but because they were less demanding about conditions. And here is the pattern that connects almost every survivor. Small size, omnivory or flexibility in diet, the ability to hide in underground burrows or at great depths, fast reproduction, no narrow specialization, everything that made an animal successful before the catastrophe, large body, specialized teeth for specific prey, dependence on a particular ecosystem, became a death sentence after it. The catastrophe didn't reward the strongest, it rewarded the most flexible. And if you think this is a lesson from the past, look at the list of species disappearing today. The most vulnerable to modern climate change are the specialized species with narrow ecological niches. Koalas that eat only eucalyptus, giant pandas that eat only bamboo, polar bears that need sea ice to survive. These are the ones going first. Exactly like the gorgonopsians and rugose corals 252 million years ago. Lystrosaurus today is the rat and the crow. Gorgonopsian today is the koala and the panda. The Permian extinction didn't end, it just changed form. And that is the most important lesson of the Great Dying, which applies not just to dinosaurs and trilobites, but to us.
Here's the question we've been holding on to this entire time, and now it's time to answer it.
Why are scientists studying events from 252 million years ago, publishing papers about the modern climate crisis? Why are paleontologists and climate scientists sitting at the same table? What do the Siberian traps have in common with today? The answer is simple and uncomfortable at the same time. The mechanisms are the same. The Permian extinction happened when volcanic eruptions in Siberia released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere, triggering large-scale climate change and ocean acidification. Now look at today. The parallels between Permian conditions and our current situation are unsettling. Rising greenhouse gases, rising ocean temperatures, ocean acidification. All of this was happening at the end of the Permian, and all of it is happening right now. But there's one critical difference: speed. The Siberian traps release carbon over tens of thousands of years. Humanity is releasing comparable quantities in just a few hundred. But what does hundreds of times faster actually mean in practice? Picture a person walking slowly on foot, and that same person in a jet. Same distance, same direction, but the speed different by several orders of magnitude. If you took all the carbon humanity has released in the last 150 years and stretched it out to the Permian pace, we'd only be at the very beginning of that process. We compressed tens of thousands of years of natural change into 150 years. A living system can't adapt fast enough. It couldn't then, it can't now. Walking pace versus a jet. And speed is the main risk. Under a business as usual scenario, by 2100, the warming of the upper ocean layer will reach 20% of the warming seen in the late Permian. By 2300, between 35 and 50%. 20% of Permian warming. And already today, corals are dying en masse. Oxygen levels in the ocean are falling. Marine ecosystems are restructuring themselves. But scientists don't study the Permian extinction just to frighten people. They study it to understand how ecosystem collapse actually happens. What signals come before a catastrophe? Where the tipping point is, after which there's no way back. And here's the detail that changes everything. Scientists studying the rocks at the Permian boundary found that 10 to 15,000 years before the peak of the extinction, the rock layers already show clear signs of stress, decline in diversity, shifts in isotopic composition, a drop in calcium carbonate organisms. All of it, a readable record of warnings. The signals were there, but there was no one who knew how to read them. We are the first species in the history of Earth that can read these signals, and we're reading them right now in real time. Research shows the Permian catastrophe didn't happen all at once. Animals and plants didn't disappear overnight. They weakened, populations shrank, reproductive success dropped, and then, at the moment conditions crossed a certain threshold, everything collapsed at once. That matters because we're seeing those same signals today. Not a catastrophe, not yet, a warning. But there's also something that gives reason for hope. The fossil record shows that after extinctions, ecosystems recovered. After ocean acidification destroyed the coral reefs, sponges that rely on silica rather than calcium turned out to be resistant to acidification and multiplied. Picture what that reef looked like a million years after the catastrophe. Empty, silent, no corals, no fish, no color, no movement, just sponges on dead limestone. They had always been background, while complex ecosystems were being built around them. And when all of that disappeared, they remained. Not because they were the best, but because they didn't need what was no longer there. Empty, silent, just sponges on dead limestone. And millions of years ahead before anything new would begin filling that emptiness. Nature finds a way, but it takes millions of years, and it happens without the species that didn't make it. What exactly does the Permian catastrophe teach us? First, the speed of change matters more than its scale. Earth has survived stronger climate shifts, but slower ones. Living systems adapted. When change happens fast, adaptation can't keep up. The speed of today's changes is the primary risk. Second, the ocean is the most vulnerable link. In the Permian, the ocean suffered more than the land. Acidification, warming, anoxia. Those same three processes are happening in today's ocean right now. Corals are the first to be hit, but corals are just the visible symptom. Behind them, entire food chains. Third, large specialized animals die first. Gorgonopsians, dimetrodons, large marine reptiles. Everything that required a stable ecosystem disappeared. Today, large mammals, elephants, rhinos, whales are the most vulnerable. That's not a coincidence. Fourth, diversity is an insurance policy. Ecosystems with high species diversity withstand shocks better. When one species disappears, another takes its place. When diversity is low, the chain breaks. The Permian catastrophe destroyed diversity, and recovery took 10 million years. Fifth, points of no return exist. In the Permian, there came a moment when the processes became self-sustaining. Heat released methane from the sea floor. Methane amplified the heat. Heat destroyed forests. Forests no longer absorbed CO2. CO2 amplified the heat, a closed loop. And there's one detail that makes this question particularly uncomfortable. Today's climate scientists are searching for the equivalent tipping points in our climate. Some believe that one of them, the thawing of permafrost releasing methane, may already have been crossed or is within reach. But there's no definitive answer. We don't know where that point is, and that uncertainty may be the most important lesson the Permian record gives us. We don't know where that point is, and not knowing may be the most important thing the Permian record is telling us. 252 million years ago, Earth went through the worst thing that had ever happened to it. It lost 96% of all marine life, 70% of all land life. It was left nearly empty, and still it came back. Lystrosaurus wandered across a devastated Pangaea and ate whatever it found. A small cynodont hid in a burrow and waited for the storm to pass. An archosaur survived the heat and the poisoned air and gave rise to the dinosaurs, and eventually to us. We're here because someone survived. Someone was flexible enough, undemanding enough, small and unremarkable enough to squeeze through the narrow throat of catastrophe. But here's what needs to be understood. Earth doesn't need us to recover. It recovered without the dinosaurs. It recovered without the Trilobites. It will recover without anyone. It has time. Millions of years. Tens of millions. The question isn't whether Earth will survive. The question is whether we will be among those who do. The Permian extinction gives us something unique. It gives us an example. A complete record of how planetary ecosystem collapse happens. From the first warning signals to total catastrophe. From catastrophe to recovery. We can read that record, study it, understand where the moments were when things could still have been stopped. The only question is whether we'll read it carefully enough.